Dear students, let us start 14th lesson, that is kinetic theory. You know that matter consists of indivisible constituents called atoms, and this was suggested by John Dalton in his atomic theory. And we know matter exists in three states: solids, liquids, and gases. As a solid, we can have an example: copper wire. Copper wire consists of copper atoms. From liquids, let us take one example: mercury. Mercury consists of mercury atoms. Here the symbol is Cu. Here the symbol is Hg. And let us take an example from gas. Helium gas consists of helium atoms. The symbol is He. But water consists of water molecules. So here where a new term molecule has come, and you know very well a molecule is made up of several atoms. For example, a water molecule, its formula is H2O. So in one water molecule, we have two hydrogen atoms and one oxygen atom. In total, it is made up of three atoms. So, one water molecule consists of three atoms. It is made up of three atoms. In each water molecule, there are two hydrogen atoms and one oxygen atom. Oxygen gas consists of oxygen molecules, and each oxygen molecule has two atoms. That's why it is called as a diatomic molecule. And there are other diatomic molecules. Hydrogen is a diatomic molecule, chlorine, nitrogen. These are other examples. If you consider ozone gas, each ozone molecule has three oxygen atoms. Three oxygen atoms. If you consider carbon dioxide gas, consists of carbon dioxide molecules, and each carbon dioxide molecule has one carbon atom and two oxygen atoms. In totally, each molecule is having three atoms. In this way, the smallest constituent in some substances is atom, and in other substances like water, oxygen, hydrogen, chlorine, nitrogen, ozone, carbon dioxide, in such substances the smallest constituent is a molecule. So matter is made up of atoms or molecules. Size of an atom is about 1 angstrom. 1 angstrom means 10 power minus 10 meters, and size means diameter. Matter exists in three states: solids, liquids, and gases, and the distance between two adjacent atoms in a solid is about 2 angstroms, and in liquids the same value. But when you consider gases, the distance between the adjacent molecules is about 10 angstroms, 5 times larger than this value. And when you consider a solid, in the solid the atoms are rigidly packed. They do not change their places, they do not move from one place to another place. But in liquid, when you come to the liquid, they can move from one place to another place. But the volume they occupy is fixed, just like a solid. But when you go to the gas, there is no limitation on its volume. It occupies as much volume as available by the process of diffusion. Since the molecules are far away from each other, the force of attraction between the molecules is negligibly small. Now, let us consider behavior of gases. At low pressures and high temperatures, a gas obeys a relation PV is equal to kT, where P is pressure, V is volume, and T is temperature, and K is a constant. K is a constant for the given sample of gas. And here the K value depends upon substance and volume. If you select a substance, for example, you have selected oxygen gas. For that K value, K will have certain value. For nitrogen, another value. For chlorine gas, another value. In that way, different gases have different K values. And afterwards, suppose you have selected oxygen gas. For oxygen gas, you have selected a gas. For the given gas, K value depends on volume of the gas, and the K value is directly proportional to the volume. But volume of a gas will be directly proportional to number of molecules. Suppose 1000 molecules occupy 1 liter volume, 2000 molecules occupy 2 liters of volume. So in this way, volume will be directly proportional to number of molecules. So from this and this, K is directly proportional to V and V is directly proportional to N. So from these two we infer that K will be directly proportional to N, or K is equal to, here we write a constant of proportionality, and that constant of proportionality is Kb. Let this is second equation. And here the constant of proportionality is known as Bolgemann constant. And the value of Bolgemann constant, its value is 1.38 into 10 to the power of minus 23 joule per Kelvin. And this value is same for any gas. See here, K value was different for different gases, but Kb value is same for any gas. Now let us substitute this value in first equation in place of K. So PV is equal to, substituting this value in first equation, we get PV is equal to, so in place of K we write KB N and here T. And this can also be written as PV by NT is equal to KB. And just now we told KB value is same for any gas. We can write P1 V1 by N1 T1 is equal to P2 V2 by N2 T2 is equal to so on. So this is for gas 1, this is for gas 2, this is for gas, like that. So this is third equation, the equation we got after substitution. And this can be taken as perfect gas equation. But when I say perfect gas equation or ideal gas equation, soon the equation you are reminded is PV is equal to mu RT. We will, that is one form of this equation. This is one form of the perfect gas equation. We will be writing several forms of perfect gas equation. So this is one form. PV is equal to KBNT. This is one form of perfect gas equation. Say this is 3A. PV is equal to KBNT. One form of perfect gas equation. And this also can be written as N is equal to PV by KBT. N is equal to PV by KBT. Now consider different gases but at same temperature and pressure. For example, let us consider different gases at NTP. NTP means what? Normal temperature and pressure. Normal temperature is 0 degree centigrade or 273 Kelvin, and normal pressure is 1 atmosphere or 1.01 into 10 to the power of 5 pascals. Okay, so you are considering different gases at this temperature and pressure. Okay, now temperature and pressure are fixed, and KB is a constant, this also fixed. Now on left hand side number of molecules and right hand side volume. So a given volume of gas will contain a certain number of molecules. Nitrogen gas, oxygen gas, chlorine gas. These are the different gases. Let us consider the three different gases with the same volume. Say suppose 22.4 liters. You have taken oxygen also 22.4 liters. You have taken chlorine gas also 22.4 liters. You have taken three different gases but same volume. If volume is same, number of molecules also will be same. Suppose in this volume there are 6.02 into 10 to the power of 23 molecules. So Here also you have the same thing. Here also you have the same thing. So when temperature and pressure are fixed, then equal volumes of different gases will have equal number of gas molecules, and this is known as Avogadro hypothesis. Equal volumes of different gases under similar conditions of temperature and pressure contain equal number of molecules. We can write the above equation in another way also. Let us take this V to right hand side and K and T to left hand side. Then the equation also can be written as N by V is equal to KT taken to left hand side, so that we get P by KBT. So the equation can also be written in this way also. Now N by V, what is its meaning? V volume has N number of molecules. Unit volume has how many number of molecules? 1 by V into N. So the number of molecules in unit volume is represented by small n, and the number of molecules in unit volume is called as number density. So n means number density. Number density means number of molecules per unit volume, and that is equal to N by V. N by V. So here N by V becomes number density is equal to P by KBT. See, under similar conditions of temperature, pressure means temperature and pressure fixed, and Kb, Bolgemann constant itself fixed. So all the three quantities are fixed means N value fixed, number density is fixed. So we can define Avogadro hypothesis in another way also. Since all these are fixed, you can write this is equal to constant or same. Now the same thing is given as a second definition for Avogadro hypothesis. How you see? The number of molecules per unit volume. The number of molecules per unit volume is same for all gases under similar conditions of temperature and pressure. This is known as Avogadro hypothesis.